Hi everyone. As a thumbnail itself saying, whenever you want to have some information, you will just open Google and searching that keyword. Have you ever think that how this happens among millions of data in Google? Now in this video, we are not discussing that very powerful and efficient algorithm of Google, but a very simple algorithm of searching an element in an integer array. So, first, let's discuss its brute force. Now, I'm taking an array and I'm inserting some values. Let's suppose 5, 3, 2, 7, 1. Now, here, what I'm going to do is uh, usually how we search an element, we will search by seeing one by one. For example, the key we want is per suppose 7. Now we will check one by one by checking like what is how it is, like we will take the loop for I equals to 0 to I is less than that length, and I plus plus, and if that a of I is equal to key, that means we will print the search found. So that is, we are checking from starting to end. Suppose if the element it is 5 and it is starting, it is the best case, that is then well and good. But what if the element is present at the end? As you know, we should always deals with the worst case, that is big O notation, and for larger inputs, that is the element if it present at the end of the array. So there will be an n iterations from I equals to 0 to at the last n. So the time complexity for this is big O of n. So let's try to reduce the time complexity here. So what I'm going to do is, first I'm doing uh, arranging the elements in an array. That is, I'm going to do here is sorting the same elements. First I will do the sort whatever the elements previously we have discussed, that is 53271. After sorting, it will be 1 2 3 5 7. Now observe the logic here. Actually here we will use the approach is divide and conquer. In the latter videos we will discuss some other examples of divide and conquer recursively, but now I'm taking here uh, for example the element we need to search the key is 2. For example, the key we need to search is 2. Then what I'm doing is, first I will take the middle element, that is middle is equal to start plus end by 2. So we know start is first, it is 1, the end is 7, so that is 1. So start index 0 1 2 3 4. So start index is 0 and ending the index is 4 by 2, that is 2. We will go to the index 2. If here for example, if that a of mid is equal to key, then we will print search found. But here, if the mid value uh, that if a of mid value is uh, less than key, for example we are searching 2 is less than 3, so then the value will obviously present from 0 to before the mid. So I'm taking here as that start is equal to mid plus 1, and else if it is greater means we will take everything from the right, that is n is equal to mid minus 1. So this is the algorithm. What we are going to do, we are dividing the big problem into sub problems. Again we are dividing. So this will the entire this will runs until while start is less than or equal to end. So I will run this code on the compiler. You can check here, you can pause the video and check the logic. So what I'm doing, I'm running. So here it search found, that is for 1 2 3 5 7. For example, key is 2, I'm searching an element, so the 2 is there, so search found. So what is the advantage for this one is, previously the algorithm, like previously what we have done is linear searching, that we are searching one by one, right? So the time complexity is order on, but now we are doing binary searching. So let's derive what is this complexity. So first iteration 1, it will be, we are checking there are n elements, but for iteration 2 we are dividing of, and iteration 3 we are again dividing n by 2 of, that is n by 4. That is we can write, for example we can write this as n power 2 power 2, this as n power 2 power 1. So at some time the by 2 power k will be, there will be only one element. So n is equal to 2 power k. I'm taking log on both sides. Log base 2 n is equal to log base to 2 power k. So I'm reversing, that is uh, log 2 base 2 power k is equals to log base to n. So power comes before, so k, and log a to base a is 1, so that is log n. So initially it is order of n, but now it is reduced to log of n. That is the time complexity has been reduced. So you can check the logic here. Actually it is nothing but just like an dictionary, we have all the words in a sorted way. If we want search word enlightenment keyword, for example, we will directly go to between d and f words and start searching. So like that, so far we have discussed how to search an integer array, any element in that. The same way we can do char array, nothing but strings. In future videos we will do this search operation in all other data structures such as linked list, binary search tree, or simply trees, and also tries. And also we will do bfs and dfs in graph.